This video is to supplement the paper, Semantic Visual Navigation by Watching YouTube Videos. Imagine looking for the restroom in one of the restaurants pictured here. Even though you don't see a restroom or a sign pointing to one in either of these images, you know that going straight in the left image is more likely to lead to a restroom than going straight in the right image. This paper seeks to learn and leverage such semantic cues for finding everyday objects like beds, chairs, couches, tables, and toilets in novel environments. The current paradigm for learning such semantic cues employs learning by direct interaction via reinforcement learning. This suffers from impractical sample complexity in sparse reward scenarios and poor generalization because of limited training environments and the sim-to-real domain gap. This paper pursues an alternative approach, where we mine for spatial co-occurrences in indoor environments by watching real estate tours from YouTube. The use of such visually diverse passive data from the internet for learning allows us to learn semantic cues for navigation in a sample-efficient manner. Such use of videos presents three unique challenges that don't arise in standard learning from demonstration. Unlike robotic demonstrations, videos on the internet don't come with any action labels. This precludes learning from demonstration or imitation learning. Furthermore, goals and intents depicted in videos are not known, so we might not know what each trajectory is a demonstration for. Even if we were to label this somehow, the depicted trajectories may not be optimal, which is a critical assumption in learning from demonstration or inverse reinforcement learning. We tackle these challenges by using an inverse model for action grounding, using off-the-shelf object detectors to label frames, and using Q-learning, which under the right conditions can learn optimal behavior from suboptimal data. Our approach, value learning from videos, starts with real estate tours from YouTube. We use an inverse model that has been trained on random actions executed by the robot to pseudo-label image frame pairs with intervening actions. We next label goal frames using an off-the-shelf detector trained on the COCO dataset. These pseudo-labeled videos are used to form Q-learning quadruples, which allow us to use Q-learning to learn a value function that can implicitly utilize semantic cues for seeking objects in novel indoor environments. Our learned value function takes in an image and object class, and predicts a value which is a proxy for the nearness to a goal object in the agent's action space. This is to say, it predicts a higher value for images oriented towards a goal object, and a lower value for images oriented away from a goal object. We can see this effect by sampling images at different orientations in the same location and visualizing the predicted values. We have such a visualization here. We can see that the predicted value for couches peaks where a couch is visible, and the value for chairs and dining tables peaks in the direction of the kitchen and dining area. The predicted value for beds and toilets peaks in the direction of the hallway, even though those classes are not visible. Additionally, we visualize the value at different locations in a heat map. Here we visualize the value for dining tables in a novel environment. We can see the value is high around dining tables, outlined in red, and it decreases as distance from the dining tables increases. We use these learned value functions for semantic navigation via a hierarchical navigation policy. It consists of a high-level policy that decides where to go by omitting a short-term goal, and a low-level policy that decides which actions to execute to achieve the short-term goal. The high-level policy builds a topological map and stores the values predicted by our value functions at different locations in different directions. It samples the most promising directions and passes a delta pose to the low-level policy. The low-level policy incrementally builds an occupancy map from a depth camera and uses the fast marching method for path planning to get actions to execute. After the low-level policy either succeeds or fails to reach the short-term goal, control is returned to the high-level policy. For learning, we collected a dataset of real estate tours from YouTube, and our experiments are conducted on a simulated robot in a visually realistic simulation environment. We study the task of finding objects of interest, beds, chairs, couches, tables, and toilets for our experiments, and use SPL and success rate as metrics. Here is a typical video from our dataset. The dataset contains 1,387 videos mined from YouTube for a total of 119 hours of real estate tours like the one shown here. We call this dataset the YouTube House Tours dataset. Here's some more examples from the dataset. We evaluate in two settings. The first is Oracle Stop, in which the episode ends automatically when the agent reaches a goal object. The second is Policy Stop, in which the agent must emit a stop action when it has reached the object. Our method is able to outperform exploration baselines and reinforcement learning with dense rewards while requiring far fewer samples of direct experience. Additionally, it outperforms behavior cloning baselines on the same video dataset. Here, we visualize the performance of our method in simulation on novel environments not seen during training. We show the RGB camera input, the depth input, the images used to determine the most recent short-term goal along with their value predictions, and a map showing the agent path in black, the current short-term goal in dark red, and the potential short-term goals in blue. Additionally, we show the location of goal objects in red. Note that this is for visualization purposes only, and the locations of goal objects are unknown to the agent at test time. Here's an episode with the goal of reaching beds. When the agent reaches this decision point, we can see that the highest predicted value is away from the living room and towards the hallway, even though no beds are visible. The agent takes this path and reaches the goal. In this episode, the agent has the goal of reaching toilets. At this point, we see the highest value towards this doorway. Again, the agent takes the right path without seeing the goal. Here, we can see the agent mistakenly go into a study while seeking beds. Because the agent continuously builds a map of the environment, it is able to backtrack efficiently and eventually reaches the goal. Finally, we show some failure cases. Our method performed most poorly on very large environments, and in environments which had visible artifacts of simulation. In this paper, we presented a technique to enable learning of semantic cues for finding objects in novel environments from in the wild YouTube videos. Our proposed technique employs cue learning on pseudo-labeled transition quadruples. This allows us to learn effective semantic cues even in the absence of action grounding and goal-directed optimal behavior. When coupled with a hierarchical navigation policy, these cues convey the agent to desired objects more effectively than competitive exploration baselines and RL methods with a fraction of the interaction cost. Code, data, and models will be made available. Thank you.